This is section 17.6, and in a way we are changing gears because we are not talking about acid-base equilibrium anymore. We are talking about solubility equilibrium, which is a case of heterogeneous equilibrium. Right? So, what is the solubility product constant? Well, if you consider an ionic substance and the ionic substance will dissolve in water, well, nothing is infinitely soluble in water. There is going to be a limit to how much you can dissolve in a particular amount of water. We have already discussed that with the solubility curves, but at any given temperature, that maximum amount of solid that you can dissolve in water is related to the KSP. So the KSP would be the product of the ion concentrations coming from that solid. Okay? Since this is a form of heterogeneous equilibrium, well, the first thing that we have to start with is the dissolution equation for that particular solid. In the case of lead iodide here, the dissolution of lead iodide involves dissolving the solid, and out of this solid you will obtain one lead 2 plus ion and two iodides. Okay, and here is very important to keep track of what the stoichiometry of this salt is, or this solid is, because we are writing an equilibrium constant for that particular dissolution. Okay, so you have the ions can regroup and form the solid, so that's the reverse reaction, so to speak. But because we have a stoichiometry here that is different from 1 to 1, you obtain two iodides here. Therefore, when you write your KSP expression, which is again an equilibrium constant, you have to consider the stoichiometric coefficients in that expression. Okay, so acid-base equilibrium was kind of easy because the stoichiometry was always 1 to 1, but when we are working with solubility equilibrium, then we have to pay attention to the stoichiometry. Different solids will have different stoichiometries. They will release a different number of ions into solution, and then you have to be aware of that. So this was the case for lead iodide. This is the expression of the solubility product constant for lead iodide. Different solids, different expressions. So let's do this one more time. Barium phosphate. In this case, the dissolution of barium phosphate. Remember, on the left side of your reaction, you will always have a solid. That is what is solubility equilibrium. And here you are obtaining 3 ions of barium 2 plus and 2 ions of phosphate, right? So this is a total of 5 ions that you are producing in solution. But again, you have a stoichiometric coefficient in each one of those ions. When you consider the concentration of those ions, then you use the stoichiometric coefficient for barium 2 plus there, which is 3, and for phosphate here, which is 2. Okay, so one thing to consider here that is going to be pretty useful for this type of equilibrium is that for every mole of salt, in this case for barium phosphate, you are producing 3 moles of barium 2 plus and 2 moles of phosphate. Now, following our tradition with ice tables and the acid-base equilibria, what this really means is that if the stoichiometry of the salt with its ions, in this case, is 1 to 3 and 1 to 2, where X moles of the salt will produce 3 times 3X barium 2 plus and 2X phosphate. Okay, so this relationship here, which comes from the stoichiometry of the of the solid, then it's going to be important at the time of writing ice tables. Okay, so the expression for KSP is going to be this one, is the product of the ions raised to the power of the corresponding stoichiometric coefficients. Remember, you have a solid in the left side of the reaction, so they do not appear in the KSP expression. It's a heterogeneous equilibrium. Solids and liquids are not considered in the expression. And remember, you have to pay attention to the stoichiometry. So, how do we calculate KSP? Well, for that, pretty much you need the equilibrium concentration, correct? So in this case, we're working with iron 2 sulfide, and we have the concentration of iron and we have the concentration of sulfide. So before we do anything, because those are concentrations, it's not like you just go ahead and multiply those concentrations. You first need your dissolution equation. So this is iron 2 sulfide, and iron 2 sulfide is simply FeS. Remember, this is going to be a solid, which is going to be in equilibrium with its ions in solution. Right? So this is the dissociation, the ionization equation for iron 2 sulfide. Therefore, based on that equation, our KSP is going to be the concentration of iron 2 plus times the concentration of sulfide. Alright, the stoichiometry is 1 to 1, so we don't have to raise to any power. And then KSP is going to be simply the concentration of iron, which is 4 10 to the negative 10, times the concentration of sulfide, which is 4 10 to the negative 10. And this is going to be 1.6 10 to the negative 9. Okay, so this is KSP for iron sulfide. Now, KSP and stoichiometry, we are saying that it depends on the stoichiometry because it's an equilibrium constant nonetheless. The solid is out of that expression, but the concentration have to be raised to the power of the corresponding stoichiometric coefficient. All right. Now, KSP, because you are multiplying, is the product of the concentration of the ions. You are assuming that at that equilibrium situation, you are pretty much with a saturated solution. Remember, it's the solid in equilibrium with a solution containing the ions. So if you have solid, the solid is not dissolving anymore. So you are with a saturated solution. So KSP gives you an idea. It's not quite the solubility of the compound, but it's a measure of the solubility of the compound. Okay? So which means if it's an equilibrium constant, the smaller the equilibrium constant, it means the less concentration you have for the ions. So it means, generally speaking, that it's less soluble. Okay, but if you want to use KSP to compare solubilities of different compounds, then you have to be careful because you can only do that if you are comparing compounds that have approximately the same stoichiometry. Now, what does that mean? Okay, so if we are comparing, for example, calcium sulfide and magnesium sulfide, then we can use KSP to compare the solubilities. Why is that? Because if you have calcium sulfide as a solid in equilibrium with its ions, then we have calcium 2 plus, and let's do this correctly, dissolved plus sulfide dissolved. And what you see here is that you have 2 ions. Okay, so the dissolution of calcium sulfide in water will give you 2 ions. Now, if you compare with that with magnesium sulfide as a solid in equilibrium with its ions, you have magnesium 2 plus, and again sulfide, and you also have here 2 ions. So the expression of KSP for these 2 solids would be pretty much the same. It's the concentration of the cation times the concentration of the sulfide. Nothing raised to the power of anything. Well, raised to the power of 1. So you can use KSP to compare the solubilities between these 2. So whoever has the smallest KSP would be the less soluble. However, if you want to do the same and you want to compare now calcium sulfide with sodium sulfide, then the thing is that now sodium sulfide in equilibrium with its ions, now you have 2 sodium ions in solution and still 1 sulfide, right? But that means that now here you have 3 ions. Okay, so this is a different This is different salt because you have a different number of ions going into solution. So the KSP is sensitive to the number of ions that you are producing in solution, and therefore you won't be able to compare KSP for calcium sulfide and sodium sulfide. So even if sodium sulfide has a smaller KSP, you can't really say that sodium sulfide is less soluble than calcium sulfide. So you have to be careful. If you have same stoichiometry, same number of ions going into solution, you can perfectly use KSP. But if not the case, then you have to be careful. Okay. So some constants that you can be using are shown here. Okay. So different values, different compounds, and I just grouped these in terms of the number of ions that you are producing in solution. For example, the first few rows here, I'm referring to those as 1, 2 solids. That means that every molecule, if you will, every particle of the solid will produce 2 ions. Okay, for example here, copper bromide will give you 1 copper and 1 bromide in solution, 2 ions total. Copper chloride, same thing, 1 copper, 1 chloride, 2 ions in solution. Copper iodide, same thing. Okay, all those, the first 5 rows in this table is solids that will produce 2 ions in solution. The next one I call it 1 to 3 solids, which means 1 particle of the solid will give you 3 ions in solution. Okay, all of them. So for example, now copper sulfide here, this is copper 1 sulfide. Now would you obtain 2 coppers and 1 sulfide there, so a total of 3 ions in solution. And last but not least, the last 2 rows in this table is 1, 4 or higher solids. So you have either, in this particular case, you have 4 ions. In the case of aluminum hydroxide, iron hydroxide, and chromium hydroxide, well, chromium 3 hydroxide. And you have also 5 ions when you look at calcium phosphate, magnesium phosphate, and barium phosphate. Okay, again, if you have a different number of ions produced in solution, you can't really compare the solubilities. But if they have the same stoichiometry, you are free to do so. So let's focus our attention now in these in copper chloride, copper bromide, and copper iodide, which are right here. All right. So we want to compare the solubility. So well, we are comparing KSPs in this case because it's the data that we have. So here, copper chloride is 172 10 to the negative 7. Copper bromide is 627 10 to the negative 9. And copper iodide is 127 10 to the negative 12. Okay? So what do we notice here? This one is the largest KSP, and this one is the smallest KSP. Since we have the same stoichiometry here, and we can just quickly review that, so CuCl as a solid will dissociate into copper 1 plus and chloride. Same thing for copper bromide, goes to copper 1 plus and 1 bromide. Same thing for copper iodide. Okay, and I want you to always do the exercise of writing the dissociation, the ionization equation for each solid. Copper 1 plus iodide. Okay, in each of these cases you produce 2 ions, so we can compare the KSPs directly. So if then we look at the KSPs and we have that copper chloride has the largest, then copper chloride will have the largest solubility, followed by copper bromide, and then copper iodide. So this is more soluble and this is less soluble. All right. So we've been talking about the KSP and the solubility. KSP is a measure of solubility, but they is not the same as the solubility. Okay, KSP is just the product of the ion concentrations. Now solubility is you are determining here amount of matter that is dissolved in a given amount of solution or in a given amount of solvent. Okay, so we can express this as grams per liter, grams per 100 milliliters, grams per 100 grams. This is what we were using in solubility curves. Okay, or we can use moles per liter. Moles per liter is something that you're familiar with already, right? Mole per liter is molarity. All right, but when we are talking in terms of solubility equilibria, this refers to the molarity of a saturated solution. Okay, so now it's not any molarity anymore, it's the molarity of the saturated solution. Okay, that is if we are referring to that as the solubility of that particular compound. So, but we can convert, since molarity is a form of concentration and you use concentration to calculate KSP, then you can convert between KSP and solubility given the proper data. So for example here for barium fluoride, we want to determine what is the molar solubility. So what is the concentration in moles per liter of a saturated solution of barium fluoride. So the KSP for this salt is 184 10 to the negative 7. And the first thing that we have to do is we have to write the solution equation, right? So the solid is in equilibrium with its ions. You obtain 2 fluorides. All right. And what do we have here at the end? Sorry, initially. Okay, initially, well, if the solid is present, then there's going to be an excess. Okay, how much is the excess? It doesn't really matter. Even if you have a 1 microgram of the solid, it's going to be in equilibrium with a saturated solution of the salt, right? But you have 0 and 0 here. Okay, now we are going to define the molar solubility as anything that is dissolving. Okay, the given amount that is being dissolved. So from that excess, I'm gonna call X the amount of the solid that is being dissolved. And of course, this is something because the solid is dissolving, is disappearing, right? So it's gonna be negative because that's the amount that is going into the solution. Okay, but at the end, let's assume that you don't have anything in solution. Okay, the solid is not in solution, so that's why it's gonna be 0. It's minus X, but that's because it's the amount that is being dissolved. But technically, you still, if you are at equilibrium, then you still have an excess. Okay, so but that means that if you're dissolving X moles of barium fluoride, then the amount of barium 2 plus that you're obtaining is X, but you are obtaining twice as much fluoride because you obtain, for every mole of barium fluoride, you obtain 2 moles of fluoride. Therefore, this is plus 2X. So you end up that at equilibrium, you will have X for barium and 2X for fluoride. Okay, now we are ready to write our equation, right? KSP is equal to the concentration of barium 2 plus times the concentration of fluoride raised to the power of 2. So here we obtain for barium is X, and for fluoride, the concentration of fluoride is going to be 2X, and that is going to be raised to the power of 2. So here is a common mistake that some people tend to do. You have a 2 here, you also have a 2 there. Okay? So you end up with KSP being equal to 4 times, because it's 2 squared, x cubed. Where does the x cubed come from? So here you have x. This becomes 4x squared. So x times 4x squared, that's 4 times x cubed. Okay? So here x now is going to be, now this is, you have to be really careful here. This is the cubic root of KSP divided by 4. Okay, so you divide by 4 the whole thing, and then you have to take the cubic root. This is going to be equal to the cubic root of KSP, which is 184 10 to the negative 7 divided by 4. And this is equal to 358 10 to the negative 3. Okay, now this is x. Okay, x is 358 10 to the negative 3 moles per liter. This is equal to the concentration of barium 2 plus as defined, but it's also equal to the solubility of barium fluoride. Okay, so that's how much barium fluoride you can dissolve in water at that temperature. Now, what if we go the other way around? So in this particular case, we use the KSP to calculate the solubility of the compound. But what if we have the solubility and then we want to calculate the KSP? So we can perfectly do that. So let's start with the first thing, right? So this is barium nitrate, and one of the things that you remember probably from 105 is that all nitrates are soluble. Well, nothing is infinitely soluble in water, and nothing is completely insoluble in water. So you may have a very small quantity dissolved in water that almost could be imperceptible, or you cannot notice it, but you cannot keep adding and adding and adding, and it will dissolve. So barium nitrate will have a limit on how much you can dissolve. So for that particular case, you can only dissolve 27.50 grams per liter. Now, if you are calculating KSP, then you need the molar solubility. And this is not molar solubility. So we need to convert that, right? So first things first, let's convert that to molar solubility. And to do that, we have 27.50 grams of barium nitrate. And we have 1 liter of solution here. For molar solubility, we still need the liter, so we are not going to do anything with that. But then we need to convert these to moles. And we convert that to moles by dividing by the molar mass. So 1 mole of barium nitrate is equal to 261.338 grams of barium nitrate. And when we do that, then we obtain that from 27.50 grams per liter of barium nitrate, we end up with a 0.1052 molar solution. Okay, so that is now the solubility that you're going to use, or the concentration that you're going to use to calculate KSP. So barium nitrate, right? You always start with a solid. Let's change colors here. You always start with a solid, and this dissolution of that solid, now it's an equilibrium. So barium 2 plus 2 nitrates. And how about we add the state, aqueous and aqueous. Okay, if we do our ice table here, okay, so we assume that this is an excess here, and we have 0 and 0 here. Since the molar solubility of barium nitrate is 0.1052, then this becomes 0.1052. So the change here in barium nitrate is minus 0.1052. So you obtain 1 mole of barium ion per barium nitrate, so this is plus 0.1052. But for nitrate is twice as much, plus 2 times 1052. All right. So this is becomes 0. This is 0.1052, and this is 0.2104. All right. So KSP is equal to the concentration of barium 2 plus times the concentration of nitrate square. So this is going to be equal to 0.1052 times 0.2104 squared. And this is going to be equal to 466 10 to the negative 3. So now this is KSP for barium nitrate. And it's kind of a rather large, for a 1 to 3 salt, this is a rather large KSP. So it's still it's more soluble than many other things around, but is not infinitely soluble. Now, in review, what is the solubility product constant? Well, it's just the product of the ion concentrations in solution. All right. It's not so simple because you have to pay attention to the stoichiometry of the dissolution, of the ionization reaction. Okay, so it's the product of those ions, but raised to the proper stoichiometric coefficients according to the balanced chemical equation. Now, the molar solubility is the number of moles that you can dissolve in 1 liter of solution. Okay, remember molar solubility. But just so that it can be easier to remember, hopefully, that is the molarity of a saturated solution of that particular compound. All right? In general, if you take a look at the value of KSP, then the lower the KSP, the lower the solubility of that particular compound. If you want to compare solubilities between different compounds, then you have to pay attention to the stoichiometry. So you can follow that trend if you have similar stoichiometries, but if not, they don't have the same stoichiometry, if they produce a different number of ions in solution, then you have to use KSP with caution. Okay.